welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1534, titled Count Good Triplets. This problem challenges us to count specific triplets in an array that satisfy given conditions. Let's dive into the details and explore the approaches to solve it. Let's continue. Let's continue. Let's continue. Let's continue. To tackle the problem of counting good triplets, we first consider the brute force approach. The intuition behind this method is straightforward, since the goal is to identify all triplets, I, J, K, that satisfy three conditions. We can systematically evaluate every possible combination of indices in the array. This involves using three nested loops to iterate over all triplets where I, J, and K are such that I less than J less than K. For each triplet, we check if the absolute differences between the array elements satisfy the given conditions. Specifically, we ensure that abs r I r j is less than or equal to a, abs r j r k is less than or equal to b, and abs r I r k is less than or equal to c. If all three conditions are met, we increment a counter. While this approach is simple to implement and directly follows the problem description, it has significant drawbacks. The time complexity is n cubed, due to the three nested loops, which makes it infeasible for larger input sizes. On the other hand, it requires no additional space, with a space complexity of 1. This trade-off between simplicity and inefficiency makes the brute force approach unsuitable for most real-world scenarios with larger arrays. Recognizing the inefficiencies of the brute force method, we can adopt an optimized approach. The key insight here is that many triplets can be ruled out early by evaluating the conditions step by step, rather than testing all three conditions for every triplet. This method begins with two nested loops that iterate over I and j such that I less than j. For each pair, I, j, we first check the condition abs, error, I, error, j, equals a. If this condition is not met, there is no need to evaluate further, allowing us to skip the remaining checks for this pair entirely. If the pair passes the first condition, we then proceed to evaluate potential k values, iterating over indices where k greater than j. For these, we check the remaining two conditions, abs, error, j, error, k, equals b and abs, error, I, error, k, equals c. If both are satisfied, the triplet is valid, and we increment the counter. While this approach still uses nested loops, it significantly reduces unnecessary checks, resulting in a time complexity of n squared asterisk m, where m represents the size of the filtered subset for each pair. The space complexity remains 1, as no additional data structures are used. This balance of improved efficiency and minimal memory usage makes the optimized approach a clear improvement, though it may still struggle with very large arrays or particularly tight constraints. Another approach worth considering involves pre-computing relationships between elements in the array to further reduce redundant calculations. The intuition here is that by pre-computing the absolute differences between all pairs of elements, we can avoid recalculating these values repeatedly during the triplet validation process. This method begins by creating a matrix of pre-computed distances, where each entry represents the absolute difference between two elements in the array. With this data in hand, we can evaluate triplets more efficiently. By referencing the pre-computed distances, we can directly check the conditions for I, j, k, without recalculating the differences. This significantly reduces redundant computations during the validation phase. However, this efficiency comes at the cost of higher memory usage. The time complexity is n squared for pre-computing distances and evaluating triplets, making it faster than the brute force approach. However, the space complexity is also n squared, as we need to store the distance matrix. While this approach can be advantageous for scenarios where memory is not a constraint, its high memory usage makes it impractical for larger arrays. Ultimately, it trades memory usage for computational speed, which may not always be feasible depending on the problem constraints. The key to improving efficiency lies in the observation that many triplets can be eliminated early by validating the conditions step by step. This realization forms the foundation of the optimized approach, which balances computational efficiency and memory usage effectively. Comparing the three strategies, the brute force method is intuitive but becomes computationally expensive for larger inputs due to its n cubed time complexity. The alternative approach with pre-computation significantly speeds up condition checking but at the cost of n² memory, which can be prohibitive in constrained environments. The optimized approach strikes the best balance by reducing unnecessary computations without requiring additional memory. This makes it both time-efficient for moderate input sizes and space-efficient enough to handle larger arrays. By avoiding redundant evaluations and keeping the implementation straightforward, the optimized approach ensures clarity and maintainability, making it the most practical choice for solving this problem. In this problem, we're tasked with finding the number of good triplets in an array. A triplet, I, J, K, is considered good if it satisfies four specific conditions. First, the indices I, J, and K must be in strictly increasing order and fall within the bounds of the array. Second, the absolute difference between the values at ARR I and ARR J must not exceed a given threshold. Third, the absolute difference between ARR J and ARR K must not exceed the threshold B. Finally, the absolute difference between ARR I and ARR K must not exceed the threshold C. The goal is to compute the total number of triplets that satisfy all these conditions, which requires careful examination of both the indices and the values at those indices. To solve this problem using a brute force approach, we begin by systematically iterating through all possible combinations of indices I, J, K in the array, making sure to maintain the order I less than J less than K. This can be achieved using three nested loops. The outer loop iterates over I from 0 to n3, the middle loop iterates over J from I plus 1 to n2, and the inner loop iterates over K from J plus 1 to n1. For each combination, we then calculate the absolute differences between the values at these indices. Specifically, we compute ARR I, ARR J, ARR J, ARR K, and ARR I, ARR K. If all three of these differences satisfy the respective thresholds A, B, and C, the triplet is considered valid. This systematic approach ensures that we check every possible triplet in the array for validity. Once we've identified a valid triplet that meets all the conditions, we increment a counter to keep track of the total number of good triplets we've found. After completing the iteration through all possible combinations of I, J, K, the counter will hold the final count of valid triplets. At this point, we simply return the value of the counter as the result. This method ensures that we account for every valid triplet in the array and provides an accurate count of good triplets. The brute force approach, while straightforward, has a significant computational cost. Since it involves three nested loops, the time complexity is n cubed, where n is the size of the array. This approach is only practical for small arrays, such as when n is less than or equal to 100. Another important detail is that the condition checking for each triplet involves three absolute difference calculations, which adds a constant factor to each iteration. While this is manageable for smaller arrays, it becomes computationally expensive for larger datasets. To address this, we can explore optimization techniques such as sorting, prefix sums, or segment trees. These methods can help reduce the number of comparisons and improve performance for larger arrays. For the brute force method, we only need the input array and a simple counter variable to track the number of valid triplets. No additional data structures are required, making the implementation straightforward. Let's consider an example to walk through the process. Given the array 3, 0, 1, 1, 9, 7, and thresholds A equals 7, B equals 2, and C equals 3, we aim to count all the good triplets in this array. By systematically applying the brute force approach, we will evaluate each triplet to see if it satisfies the conditions. Let's look at the first few triplets in detail. For the triplet, I equals 0, J equals 1, K equals 2, the values are ARR 0 equals 3, ARR 1 equals 0, and ARR 2 equals 1. The absolute differences are 3, 0 equals 3, 0, 1 equals 1, and 3, 1 equals 2. These satisfy the thresholds A equals 7, B equals 2, and C equals 3, so this triplet is valid, and we increment the count. Next, for the triplet, I equals 0, J equals 1, K equals 3, the values are again 3, 0, 1, with the same differences, 3, 0 equals 3, 0, 1 equals 1, and 3, 1 equals 2. This triplet is also valid, so we increment the count again. This process continues as we evaluate all combinations of indices and verify whether they satisfy the conditions. After iterating through all possible combinations of I, j, k, we find that the total number of good triplets for this example is 4. This final count is returned as the output. While the brute force approach ensures accuracy, it's worth exploring alternative methods for larger datasets to improve efficiency. With this understanding, you now have a clear strategy for solving the count good triplets problem. This Python implementation solves LeetCode problem number 1534, count good triplets. The solution employs a brute force approach by iterating through all possible triplets in the input array. The count good triplets method takes 4 arguments, the array ARR and 3 integers, a, b, and c. The goal is to count triplets, I, j, k, that satisfy the given conditions. First, we determine the length of the array n and initialize a counter good underscore triplets to 0. This counter keeps track of the number of valid triplets. The algorithm uses 3 nested loops to iterate over all possible triplets, I, j, k, ensuring that 0 equals I less than j less than k less than n. The outermost loop selects the first index I, the middle loop selects the second index j, and the innermost loop selects the third index k. For each triplet, we evaluate the 3 conditions in sequence. If the first condition, ARR, I, ARR, j, equals a, is not met, the inner loops are skipped using a continue statement. This optimization prevents unnecessary computations for invalid triplets. If the first condition is satisfied, the second condition, ARR, j, ARR, k, equals b, is checked. Similarly, if this condition fails, the innermost loop is skipped. Finally, if both prior conditions are met, the third condition, ARR, I, ARR, k, equals c, is evaluated. If all 3 conditions hold true, the triplet is valid, and the good underscore triplets counter is increment. The function returns the total count of good triplets after all iterations. Although this approach has a time complexity of O(n) cubed, due to the triple nested loops, it is straightforward and ensures correctness for small to moderate input sizes within problem constraints. Here, we have the Java implementation for counting good triplets. We begin by defining the method countGoodTriplets, which takes an integer array ARR and 3 integer parameters a, b, and c. Inside the method, we initialize the variable n to store the length of the array and a counter good triplets to keep track of the number of valid triplets we find. Next, we use 3 nested loops to iterate over all possible triplets, I, j, k, in the array. The outer loop starts with I, iterating until n to 2, because we need at least 3 elements for a triplet. The middle loop, with j, begins at I plus 1 and runs until n1, ensuring that j is always after I. Inside the second loop, we first check the condition ARR, I, ARR, j, equals a. If this condition is not met, we skip the current iteration using the continue statement, as the triplet cannot be valid. If it passes, we proceed to the innermost loop, where k starts at j plus 1 and iterates until the end of the array. In the innermost loop, we first check the second condition, ARR, j, ARR, k, equals b. If this condition fails, we use continue again to skip to the next iteration of k. However, if it holds, we move on to the final condition, ARR, I, ARR, k, equals c. If this third condition is satisfied, we increment the good triplets counter, as this means the current triplet, I, j, k, meets all the criteria. After all the loops have completed, the method returns the total count of good triplets. This implementation ensures that every possible triplet is checked while adhering to the given constraints, and the use of nested loops and conditionals allows for a straightforward and readable solution. To solve the problem, we start by initializing 2 variables. First, we calculate the length of the array, which is 6 in this example, and assign it to n. Then, we initialize good underscore triplets to 0, which will store our final count of valid triplets. We begin with the outer loop, where I is set to 0, representing the first element of our triplet. The value of ARR, I, is 3. Moving into the middle loop, j is set to 1, representing the second element, and ARR, j, is 0. At this point, we check the first condition, the absolute difference between ARR, I, and ARR, j, which is a 3, 0. Since this equals 3 and is less than or equal to a 7, we proceed to the inner loop. Here, k is set to 2, representing the third element, and ARR, k, is 1. We now validate the second condition, ARR, j, RR, k, equals 0, 1, which equals 1 and is less than or equal to b, 2. Finally, we check the third condition, k equals a 3, 1, which equals 2 and is less than or equal to c, 3. Since all three conditions are satisfied, we increment good underscore triplets to 1. With k increment to 3, the next value of k is 1. The second condition is checked, k equals 0, 1, which equals 1 and satisfies the constraint be less than or equal to 2. The third condition, k equals 3, 1, also equals 2, satisfying c less than or equal to 3. Once again, all conditions are met, so we increment good underscore triplets to 2. Moving to k equals 4, where k is 9, we calculate k equals 0, 9, which equals 9. This exceeds b, 2, so we skip further checks and continue to k equals 5. Here, k is 7, and k equals 0, 7 equals 7, which also exceeds b, so we skip again. We then continue with the middle loop, setting j equals 2. Now j equals 1, and the first condition, j equals 3, 1 equals 2, satisfying a less than or equal to 7. For k equals 3, where k is 1, we check k equals 1, 1, which equals 0 and satisfies b less than or equal to 2. The third condition, k equals 3, 1 equals 2, satisfying c less than or equal to 3. All conditions are met, so we increment good underscore triplets to 3. Continuing with k equals 4, where k is 9, we calculate k equals 1 and 9, which equals 8 and exceeds b, 2. Thus, we skip to k equals 5. Here, k is 7, and k equals 1, 7 equals 6, which also exceeds b. Returning to the middle loop with j equals 3, j is 1. The first condition, j equals 3, 1 equals 2 and satisfies a less than or equal to 7. For k equals 4, where k is 9, we calculate k equals 1 and 9, which equals 8 and exceeds b. Similarly, for k equals 5, where k is 7, k equals 6, which also exceeds b. At this point, we repeat these steps for the subsequent values of I, 1, 2, 3, and 4. Each iteration follows the same logic, updating good underscore triplets whenever all conditions are met. After all iterations, the total count of good triplets is determined to be 4. In this second example, we use the array 1, 1, 2, 2, 3, and constraints a equals 1, b equals 1, and c equals 2. We begin by initializing the length of the array, n equals 5, and setting good underscore triplets to 0. Starting with I equals 0, I is 1. For the middle loop, j equals 1, and j is also 1. The first condition, j equals 1, 1 equals 0 and satisfies a less than or equal to 1. Moving to the inner loop where k equals 2, k is 2. The second condition, k equals 1 to 2 equals 1 and satisfies b less than or equal to 1. The third condition, k equals 1 to 2 equals 1 and satisfies c less than or equal to 2. All conditions are met, so we increment good underscore triplets to 1. Next, for k equals 3, where k is 2, the second condition, k equals 1 to 2 equals 1 and satisfies b less than or equal to 1. The third condition, k equals 1 to 2, also equals 1 and satisfies c less than or equal to 2. Thus, we increment good underscore triplets to 2. We then repeat these steps for I equals 1, 2, and 3, following the same process of checking all conditions for each triplet, I, j, k, and updating good underscore triplets whenever they are satisfied. By the end of the iterations, the total count of good triplets is 4. This solution systematically iterates through all possible triplets, I, j, k, or I less than j less than k, ensuring that every unique triplet is considered. By verifying the conditions sequentially, we minimize unnecessary computations and skip checks as soon as a condition fails. The algorithm has a time complexity of O, in superscript 3, due to the triple nested loop structure, making it suitable for small arrays. However, for larger inputs, further optimizations may be needed, such as pre-computing condition checks or leveraging data structures for faster lookups. While the current approach is straightforward and guarantees correctness, exploring improvements for scalability can be a valuable exercise. To begin analyzing the time complexity, let's look at the structure of the algorithm. The first loop iterates through the array from index I equals 0 to n3. Since this loop runs for approximately n2 iterations, it has a time complexity of O(n). Next, within this outer loop, there's a second loop that runs from j equals I plus 1 to n2. For a given I, this second loop executes about ni2 times. If we sum this over all values of I, it forms a series that simplifies to n2, n1/2, which is O(n squared). After that, the innermost loop iterates from k equals j plus 1 to n1. For each pair of I and j, this loop runs about nj1 times. Summing over all pairs I, j, the total number of iterations becomes n2, n1/6, which scales as O(n cubed). This nested loop structure, therefore, dominates the time complexity of the algorithm. Within the innermost loop, the algorithm evaluates three condition checks: error I, error j equals A, error j, error k equals B, and error I, error k equals C. Each of these checks is a constant time operation, or O(1). Since these checks are performed for every triplet iteration, their contribution is effectively absorbed into the overall complexity of the nested loops. Putting it all together, the time complexity of the algorithm in the worst case is O(n cubed). Moving to space complexity, the algorithm primarily uses the input array ARR of size n, which requires O(n) space. Aside from this, auxiliary variables like loop indices and counters consume only a constant amount of memory, or O(1). As there are no additional data structures or memory allocations based on input size, the total space complexity is O(n). Furthermore, we can evaluate specific cases. In the best case, if the input size n is very small, the algorithm still has a complexity of O(n cubed, but the actual number of iterations is minimal. In the average case, the algorithm consistently evaluates all possible triplets, resulting in the same O(n cubed time complexity. For the worst case, all conditions are satisfied, and the algorithm examines every one of the O(n cubed triplets. Comparing this brute force approach to potential optimizations, we see that while this method directly evaluates all triplets, optimized approaches could reduce the number of iterations or checks. For example, using sorting combined with binary search or pre-computing valid ranges could lower the time complexity to O(n squared log n, or better, depending on the constraints. However, no such optimizations are implemented here. Finally, the O(n cubed time complexity can be mathematically justified. The algorithm evaluates all combinations of triplets, I, j, k, or I less than j less than k. Using the combination formula C, n, 3, equals n, n1, n2/6, we observe that the total number of triplets matches the nested loop structure, reaffirming the cubic time complexity. When working with this problem, there are some common mistakes you should watch out for. First, incorrect triplet indexing can be a major issue. If you select triplets where indices do not follow the order I less than j less than k, such as when I is greater than or equal to j or j is greater than or equal to k, you'll violate the conditions specified in the problem. This will inevitably lead to incorrect results. Next, ignoring edge cases is another frequent pitfall. For example, if the input array has fewer than 3 elements, it's impossible to form a valid triplet, and failing to handle this scenario can result in index errors. Similarly, arrays with repeated elements can trip up your logic if you don't account for duplicates properly. Lastly, it's easy to overlook constraints when validating triplets. If you only partially check the conditions, such as verifying one or two constraints while ignoring the others, you risk counting invalid triplets. Ensuring that all conditions, including the bounds on absolute differences, are met is crucial to solving this problem accurately. Now, let's discuss additional challenges that often come up and how to address them. Inefficient approaches, particularly brute force, can be problematic for large inputs. While brute force is simple to implement, its O(n cubed time complexity becomes impractical when the input size, n, grows large, say, up to 10 cubed elements. Optimizing your solution is essential for handling these larger datasets. Another common issue is misinterpreting the absolute value constraints. If you calculate differences like ARR, I, ARR, J, without taking the absolute value, you'll miss valid triplets where the subtraction order matters. Beyond these specific mistakes, it's helpful to keep some key insights in mind for interviews. Triplet problems often follow recognizable patterns, such as requiring I less than J less than K and placing bounds on differences. Efficient solutions frequently involve nested loops, sliding windows, or other optimization techniques. For large constraints, be prepared to discuss ways to reduce complexity, such as sorting or using prefix sums. Finally, always consider edge cases and clearly communicate trade-offs between approaches, like brute force versus optimized solutions, to demonstrate your problem-solving process effectively. Now let's explore related problems and alternative approaches to solving triplet-based questions. For additional practice, problems like LeetCode 15, 3-sum, LeetCode 16, 3-sum closest, LeetCode 18, 4-sum, and LeetCode 611, valid triangle number, all involve similar concepts and constraints. Tackling these will deepen your understanding of how to approach variations of this problem. As for solving strategies, brute force is the most straightforward approach, iterating through all possible triplets, I, J, K, and validating the conditions. While this is easy to implement, the O(n)³ time complexity makes it unsuitable for larger inputs. An optimized approach involves sorting the array and then using techniques like two-pointers or binary search to efficiently identify valid triplets. This significantly reduces complexity to O(n)² log n, or even O(n)², but it does require more sophisticated implementation. In some cases, sliding window techniques can be applied to maintain valid ranges for indices dynamically. This method is highly efficient under certain constraints, though it may not be directly applicable to all triplet problems. By understanding these alternatives, you can adapt your solution to meet varying requirements effectively. To wrap up, we reviewed the problem, explored different approaches, and learned valuable lessons about optimizing solutions. I hope this walkthrough helped you better understand the problem and the thought process behind solving it. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!